presentations. Here is the presentation outline. We will present on productions, the methodology, the resources used, and the vehicle design, ticket place implementation, target and obstacle detections will address. So, as an introduction, a pick-and-place system designed to perform the task of picking of objects from one position and placing them in the other. It consists of multiple segments connected and is equipped with motors, sensors, and grippers. As you can see this here on the screen. Here the methods we used to do this project. In phase one, we designed and manufactured the mechanical gripper and assembled the gripper on the Heaven robot. Then we specified the pick and place positions, then determined the corresponding angular positions of each joint in the two positions. Then we write the program to control or to manipulate the robot. After all, we evaluate the system at this phase. In the second phase, we apply object detection using a 2D camera, and we try to calibrate the camera. And we map the camera coordinate to the robot coordinate system. We write the program, then we manipulate the robot. Then we try to apply obstacle detection mechanism. Here are the resources we used for our project. We used SolidWorks to design the gripper and Visual Studio to program the robot, Arduino Uno power supplies, and 3D printers, servo motor we used, and 2D camera and the manipulator and other tools necessary to build the robot gripper. In the gripper design, the most common purpose of the gripper or the interpreter is to grasp or enclose parts for transfer, insertion, or assembly. So the factors considered during design to ensure a proper gripping are the part shape, accessibility, and part consistency, part weight, orientation, and dimensions of the part to be gripped, the size of the object to be gripped, and the grip on or open or grip close. So this is the assembly model and the prototype. Our gripper has a 200 millimeter head and the 80 millimeters gripping nominal width. So after modeling successfully, we directly go to manufacture the parts in a 3D printer and we assemble it. After assembling the object, we write the program and try to check how it works, the mechanism. So the driving motor is a servo motor, and controlling on the servo positions at different parts, we can open and close the gripper to catch the objects. And after completing the manufacturing the gripper, we directly go to assembling on the Highwind robot arm. Then we directly go to pick and place implementation for the using our gripper. We write the program using C++ to control our manipulator. And finally, we get to control or to pick and place the objects this way. Now, initially we have the pick position and the place position. Here, due to the misalignments and some problems, our paper has failed to catch this object, and we fix the problem in the next. We fix the problems with our gripper and go for the test next. So in the next already we were successful to pick and place the object. Now it's successfully gripped the object and placed it in the desired position. Okay. So this way it works, and after accomplishing this task, we directly go to applying an object. In the second phase, the target or the object detection and obstacle avoidance. So in the target, and because the previous one is based on we specify the place and peak positions, but if we change the position, the robot has no option to detect the object and to work with. So in order to solve this problem, we try to detect the object using color detection. For this, we follow this workflow. We start to capture the image, and we apply color detection using OpenCV, and position and orientation will be determined from the detected object. With this, we'll determine the coordinate transformation from the camera coordinate to the robot coordinate, and directly we'll go for robot operation. The camera with the program will check if the object is available on the table. If no object, the process will end. If there is object, it will start over and over until the whole object will finish. So we put this way the objects, different types of objects with different colors, and we set the camera on the above at a 70 millimeter, and we apply the object detection or color detection, and here the angles of the objects from the camera coordinate has indicated this way. And next we go for calibration of the robot and the camera, and after doing these things, we directly go for applying or manipulating the robot. So it works this way, and it was successful. In this case, wherever we put the object, it detects automatically, and it can go there and pick it and to place to the desired position. Sorry for the vibration of the video. and we add another object. Now the camera has detected it, and there is an object on the table, so it will come to the first step to grip this object in place. Then we'll add another object. Then it will detect the object, its position and orientation, and it will come and take it. Yeah, we add another object here. And it plays on. Now the table is already finished. This way it detects and works. Next, we'll try to. We have tried to apply obstacle avoidance, and my friend will continue.
Next is talking about obstacle detection. And machines are employed to replace text with high levels of repetition since they do not get tired and can maintain a constantly high level of precision. With the correct input commands, machine can operate autonomously, allowing one person to oversee multiple workstations simultaneously. However, in this process, typical robotics lack perception. So, if obstacles enter the production line, it may lead to machine stop or damage. And one person responsible for numerous machines may struggle to address issues promptly. Given this scenario, we propose this obstacle detection. And here is the flow chart. And I will talk about the sensor part. And I use Arduino to control the sensor. And the sensor we use is ultrasonic sensor. And we connect 3 sensors because we want to put the sensors on the left and right and front of the arm. And we change the buzzer first to make the different sound. And here is the sensor model design. And you can see here is 3 ultrasonic sensor, and here is the buzzer. And here is the video of our sensor. And you can see that when the obstacle goes near to the sensor, then it will make different noise because I want to let the user can hear the sound to know where is the obstacle. And yet not infected to the actual robot due to the shortage of. And here is the sensor code. And this part is for the sensor to sensing the position of obstacles. And here is to calculate the distance between the obstacle and the sensor. And here it will print out the value, and when the value is less than the 100 millimeter, then it will make the user to make the noise. And I change different hertz to make it have different sound. And that's our project. Thank you.
Okay. So I think your team did a very good job. You integrated multiple systems. You have you designed a gripper with 3D printing, Arduino control, motors, and then you use image processing to identify the object so you can grasp it. Then you talk about obstacle avoidance with ultrasonic sensing. So I have some small questions just to make sure I understand what has been done. So can you move to the linkage design for your gripper? The 4-bar linkage, yes. So why did you choose this geometrical design and also the length? Why this one?
Because this can give us a wider range to grip, and this shape is in order to accommodate for circular objects.
Okay. Usually when you have like a gripper design, there is like a goal for your design, like a purpose. So I think this part is a little missing. You didn't mention, okay, do you want to have a gripper that moves in parallel, or it's actually doing something like this, and what's the requirement for the design? So I know you can figure out what exactly you're looking for, but in your presentation, this part is a little lacking. So I recommend you in the final report, you can mention more about why you pick up this design. Okay, I know it's a very common design. And also at the finger part, there is a curvature at the inner side. I know you could use it to grasp something like a sphere or like a cylinder, but that's also one design concept, right? So that's also something you need to mention why you do this. And if you truly have this curved geometry, then you can show you can truly grasp like a cup or something like that in the design. Okay? Yeah. Since you recognize multiple kinds of objects with different shapes, how do you know how much motor motion is needed for every grasping? It's like a predefined angle, or you compute how much you grasp?
No, just.
So maybe you can show one of the page of your image processing. Go further. Like this over here. So you have several detection boxes.
Yeah.
If one day I put a new box with a different size, does that detection tells you how much you should grasp?
Yeah, it can tell me, but I have to specify all the detected objects
In advance.
Yeah.
I see. So I think in the future, if you later on when you write a report, you can try to figure out the size of your detection box and how much you grasp. I believe you can find some kind of relationship. So in the future, if you have a detection of different objects, maybe you can already know how much you should grasp, because it's depending on the geometry, the size, right?
Yeah, actually, for this case also, already we know the size and the dimension or the orientation of the
object. But if I give you a new object, then the size is unknown. Of course, you can use image processing to realize the diameter. And what I'm saying is, I hope this could be an automated process so that your system already know, okay, when I grasp, I should actuate how much. So it's not yet completely, it's not completely automatic. So it actually can be automatic. So final thing about the obstacle avoidance. I didn't see where you put the ultrasonic sensor. Is it somewhere on the pump? So not integrated yet.
Yeah, we didn't.
Okay. Yeah, maybe in the final report you can try it. Maybe you can just put somewhere on the robot. So far, the detection triggers a buzzer.
Yeah.
Maybe you can use that signal to trigger more robot control. So if you are in danger of contacting something, at least stop.
Yeah, to stop and
Yeah.
wait as soon when it detects some obstacle to give buzzer and stop the movement of the robot. And for this stage, somebody human can come and remove the obstacle.
So since you have different sensors, if you have a sensor here and your next motion doesn't even rotate this part of the arm, that means I can continue to move here. Because the obstacle is here, I'm not moving here anymore. So if you have a detection here, that means I can still move like this, right? So since you have multiple sensors, you can realize which part could be contacting with something, and you can check whether this part of the body is gonna move. If not, maybe you already finished the movement right here, so we can do some other movements. Yeah. So you can. I know probably you don't have enough time to complete everything, but since you bring up the idea of multiple sensors, then why don't you at least elaborate how it could be used in the final.
Yeah.
So just one more question, that how did you define the 3D position of your objects? How did you define your 3D position as your objects? Because it seems as if there are one video shows that when you take that object and then incline. So it seems the gripping position is not a match sample. And I just wonder, so how do you define it?
Actually, that's not because of the gripping position. The gripping position already we defined it successfully, but the problem were due to the grip. The gripper couldn't grip just firmly and after it grips, because after it grips already, since it was loosened when it tries to pick it, it was about to incline.
Why? The friction? Because of
It's from we have no just enough torque to grip that object from the servo motor. When we give much more torque to the servo overlocks and it creates another problem. So we slightly give a minimum amount of torque, and that torque, since we have no enough friction between the two objects, it grips and we try to move it. That's due to that problem, not due to the 3D position.
Okay, thank you. Let's move on to the next team. So where is your third teammate?
We have two.
Only two?
Yeah.
So Kang Ding-Jen, she dropped? Okay.
Hello, professors, and here are our final project. It is about positive benefit using fully autonomous path planning for robotic manipulator. And here is our movement. So this is our outline for the presentation. For the introduction parts, and our goal is to move the box from the initial pellets to the final pellets. And in the past, there's an obstacle between them. and the path of the moving box is fully autonomous, so it is not fixed and is flexible due to the obstacle. And in the right-hand side of the picture, you can see our configuration in our lab. So the right-hand side palette is the initial palette, and the left-hand side, the iron color one, is the final palette. And we didn't picture out the obstacles in between, but it is in front of the machine arm. And here's our hardware for the lab. So we use the Highwind RS620 for robotic arm with the architecture of such a device. And we cooperate with 2D camera of Real D435 with the coding software of Visual Studio 2019, and the programming language is in C++. So for bugs recognition, we will start by the 3D camera to see if there's any bugs in the initial palette. And if there's no bugs there, then we'll just end the device. And if there's some bugs on the palette, we will get the point cloud by the camera. And because it is 3D camera, so we can get the Z value. And after getting the data, we will do downsampling to faster the calculation speed. And then we do the clustering to extract the features that we want. And after that, we will print the 3D projection to the 2D image. And by the 2D image, we can find the edge. And then we use morphology, and finally we do the bounding the box. And we will know the center of the box, then we can actuate the motion of the arm, and then we can go to the end. So by this process, we can get the point cloud. As I said, in the green one, gets the point cloud. It is the first one. So after we're getting all the point cloud, the second step is to do the downsampling, as I said here. So by downsampling, you can see that the feature is remaining, while we can lower the data numbers so that the calculation will be faster. And for the clustering, we can extract the 3D, the part that we want. And because this image is 3D, so we will transfer it to a 2D image, as I said in the blue parts, the first one. And then after getting the 2D image, we can form a boundary, and then finally we can know the center of the box. And because we already done the hand-eye collaboration from the 3D camera to the arm, so once we know the centers in the camera, we can use homogeneous transformation to know the box location with respect to the arm. Yeah. So this part I will give Andy to explain this.
Okay, so after we know how to detect the boxes to do the image processing, then the next one is we can try to do to solve the pipelining. So we're going to use GA for the pipelining. So this is the flow chart of the GA program. So first we generate an initial population, and after that we can calculate the fitness value, and then after that we check the termination condition. So after we iterate for 15 generations, we will end the GA program. And after that we can do the GA algorithm, which is the selection, crossover, and then the mutation. So for the individual of this GA program, so we say that we have a variable x as the individual. So this individual s, it contains 6 points. So from P1, P2, P3 until Pn. And each of these P points, we have the x, y, z coordinate of this point. So we are going to generate. Actually, we only generate 4 random points, because the first P1 is the starting point and the Pn or P6 is the end point. And then for the selection method, we are going to use the elite selection. So we are going to choose the top 5% of the shortest distance. And then for the crossover method, we are going to choose the multi-point crossover. So for example, we have this father as the orange DNA and then the mother as the blue. So the child will have the combination of the father and the mother. So the child will have the color of blue, orange, blue, orange, blue, orange. And then for the mutation method, we are going to choose 10% mutation probability for each individuals. And for the next one is we are going to give a penalty for the obstacle avoidance. So first we are going to design a safety wall for the box and the obstacle right here. So this red line, the red color here is the safety bulb for the box and obstacle with the radius of R box and R obs. And then, for example, we are going to move this box along this red path here. So we can calculate the shortest distance, which is the shortest distance between the red line here and the obstacle. So we call it the D variable. And then if the D variable here is the value is less than ds, where the ds is the addition of the R box and the plus R ops plus D safety, where the D safety is 100 millimeters, then we will give a penalty for the individual. And then the next one is we are also going to give a penalty for the inverse kinematic. So we will check each individual if the points that has been generated, if it is reachable or not. Then if we cannot solve it by using the inverse kinematics, we will give a penalty with a value of 100,000. And then the next one is we are going to calculate the sum of path length. So basically this is the distance traveled by the n effector. So this is the equation that we are going to use for the calculation. And then this is the final fitness value for the GA program. And then this is the simulation result that we have done in the Python program. So this in the left figure here, this is the generations with the best fitness that is printed right here. And these 6 lines here, this is the 6 points that have been generated, the optimal points that have been generated by using the GA program. Yeah, so this is the simulation result. So this green one here is the robot, and then the pile of boxes, this is the box, and this big box right here is the obstacle, and we want to move this box into this the end point there. And then finally, we try to do it in the real experiment. So we try to move this pile of boxes here into this table. So after we place it on the table, we have to manually pick up the box by ourselves. And then after we finish the first layer here, there's going to be a little bit of long pause here because we need to solve the GA and all of the image processing first. And because we are using CPU to solve it, so it's a little bit slow. So if we use GPU, it might be faster. So yeah. We also tried another one for our experiment. So as you can see that it is actually pretty robust. It successfully picked up the box and successfully put it on the table. Okay, so yeah, that's all from our experiment. So in conclusion, so the number of path points was reduced to lower the computational cost, and it's result in sufficiently smooth path. And the smoothness of the path can be optimized through post-processing methods such as interpolation. We can also try to implement using GPU to improve the computational efficiency, which enables increasing the number of path points and making the path more smooth. And that's all from our presentation. Thank you.
Okay, so very great. One suggestion, you didn't mention about how you complete the hand-eye calibration. I think in the final report, please mention how it was done. I know it's quite standard, but
Yeah.
it's a part of the project.
Yeah.
But is it done by the lab already, or you guys redo it? So you do it in the course, not from the past.
No, in the course.
Oh, okay. That's nice. That's very great. Okay, so I know it's not a optimization course, but I'm very curious about your GA. Can you move on to the chromosome part? I'm not very sure about what does your chromosome look like. Is S your chromosome?
Yeah, as is in the individual diagram.
S is your chromosome.
Yeah.
Okay, so basically you are looking for multiple intermediate points.
Yes.
Okay. Is it how many degree of freedom for the points? Only 3?
Only 3. Yeah. We only put the X, Y, Z.
How about orientation?
因为那个我们要让那个，我们为了确保我们的这个棒式它是垂直向下的，所以我们 R X R Y 是固定的。
Okay.
对，然后 R Z 的话是由那个相似变化是由相机去判断的，所以目标位置它的 R Z 固定，所以我们过程中 R X R Y 都固定 ，R D 是计算，就是后项计算这样。
By GA? Calculated by GA?
没有，不是固定的，就是从这个变化到这边，然后用就是固定方式。
Okay, so use GA to find the XYZ point, and then use image processing to realize the rotation. Yes, right?
Yes.
See, it's not so hard. You can use it. Okay, go back. So can you explain again about the fitness value? So are you looking for larger fitness or lower? Anyone can answer. Larger fitness or lower fitness? Okay, I know you are the designer, you are the presenter. So you don't know the answer. Okay.
就是我们会选择 fitness 是比较好的，因为
larger better or lower better?
larger better.
Larger is better. Okay. So larger is better. That means smaller L, smaller PA, smaller PIK. Smaller L means smaller sum of path. PA, what is PA? Smaller penalty. So if there's a collision, you penalize it. So you are looking for a path that doesn't collide.
Yes.
Okay. How about the PIK?
This is the inverse kinematics. So we check if the points are solvable using IK or not.
I see. Interesting. Okay. Can you move go down? Okay. Usually, GA needs to you need to run GA for 100 iteration or even more. 15 looks too not enough. Usually, we need more iteration.
因为我把那个 population 的数量把它拉回来。
Even you do that, you still need very long period of time to make sure it's up there. Even though you have large population, I still recommend you run it for longer. Try this in your final report. Just run, for example, run this for 100 iterations. See what happens. Maybe there is a better. You know, GA will do this. The fitness goes up, and then it stays there for a long time, and suddenly you have another jump. Because it's a random process. It needs some time to get lucky. So the luck doesn't come every iteration. So the iteration process is always like this. It's not converged yet. You need to give it a long time to do it. And if you feel like the process is taking too long, you can reduce the number of population because many of your population is garbage. So if you create a lot of garbage, then you're wasting time to process the garbage. Okay, very nice. Okay, about how the robot goes back. Is it by GA?
Yes.
So your GA includes forward movement and backward movement.
Yes.
So one of your the minimized path also includes the backward movement. That's pretty good. Okay, thank you.
Well, I just wonder that because you mentioned that you will use the camera and then get the image from the computer. However, how can you translate the image into the point cloud? How can you get the vertical distance?
因为那个 real sense 里面 library 可以解释，那个 real sense 它有 library 可以直接转换到影像。
But it seems that you just get a place, you just get the top view, and how about the vertical distance?
It's a 3D camera.
3D camera.
Real sense is a 3D camera. So they know the.
Why? But why? Because that is the image you get, and then.
哎，这个是电影，这个部分是电影。
It's a 3D point cloud.
Yeah, and then how do you know the height of the box? Even though that is a 3D camera.
The thickness, the height of the box.
就是
Predefined, right?
他负责，他跟前人负责的，就是相对容易。
Yeah. How do you know how tall the box is? The box can be this tall, the box can be this tall. So if you have a tall box, when you grasp it, you may hit the table. So what Professor Chen said, maybe your box has the same height, right? It's a predefined. 先设定好是吗? So if we put different box with different height, this system doesn't work. 对不对？如果放了不同高度的箱子，就完蛋了，是吗？对。来，
我要怎么解释？
就给你
就是因为我们那个 real sense 它可以知道点到相机之间的它们的外部参数。对，那我们从点
you don't know, you only see the top.
对，我们找
So you don't know what's going on underneath, below it. You don't know.
对
So when you take it, you don't know how tall it is. So if I give you a very tall box, then you will hit the table. Right? So how do you know this? You have to fix the number.
对，这部分比
So in the future, if I give you different sizes, then it's a problem. Yeah, it's a problem. It's okay. It's okay to have problems. So maybe in this kind of problem, you need a second camera to realize the height. Then that's solved. Don't worry. But it's a very good point. If you want, you can try this in your final week. Okay, great, thank you. So next.
our outlets. And the first introduction. So the robot arm is the robot manipulate the visually programmable with similar function to a human arm. So the distinction in the industry suffer mental issues operating hours working deficits. So in industry force, we can join robotic arm the system to increase production capacity. So our goal is to add robot arm to assist people by work concept. And in battery product, we use the camera to image recognition and some the object to move the intelligent antenna or a triangle object to move the triangle connector. This robot is just P2P to move the object to the position. And we use the camera to recognition images and to some use the AI machine learning models to cover sorting process. And our progress focus on sorting the objects according to its shape. Okay, I will introduce the experience setup. We use the camera is GoPro Hero 9 and we use the robot Arduino open source robot and controlled by the Arduino board, and with our object and back cylinder and blue cube and damaged object. And this is our setup, the camera and the robot position. And this is our robot workspace. It's 200 millimeter times 300 millimeter. And this is our, we set the 3 initial position. This is the first initial position, and this is the second initial position, and this is the third initial position. We will put the object in random, and we use the machine learning to identify the object and put the back cylinder in the end point, the position, and blue cube in end position. And damaged object we will put in this position. And we use the image recognition and we use the technical mechanic to machine learning, and we get the object characteristic .h5 file, and we put in the OpenCV library and obtain the object result. And program communication, the image recognition we will put in the Python and convert to Arduino code, and we will execute the robot pass HTML file and the robot in action. This is a program flow. The camera and image recognition, and if yes, you will assist the object. If no, the robot will return the original. And if you identify the cylinder, you will execute the pass 1. If no, you will identify the another object.
The next is result. After my friends has, after our team has set up the experiment for our final project, this is the result. We have the 5 case, which is one case to another is different. The difference is from the only in initial position and this is for the case 1, which the initial position is in the left hand side of the robot arm, and we'll place to the right hand side of the robot arm, which is this position is the end position of our final project. And then for the case 2, the robot arm will move the blue box because the blue box is not exactly in the end position. Okay, and the black box is in the initial position, same as in the case 1. As you can see, the robot arm will move the 2 objects to the end position. And going to the case number 3, this is the same with the case number 2, just we swap the blue box and the black box. Okay, and the case 4, the blue box is in the random position, and as you can see, the robot arm will move to the end position, and the black box is not exactly in the end position. And the last case is we add another object, which is the green box, which we don't want it in our final project, and I will say it will filter the unwanted object, and the green box will place to the match position.
Okay, so conclusion, our team classify and identify items, use robotics arm and image machine learning, and this is our result.
So in your case 2, I saw the robot arm grasp, I think the blue object, I think the case 2. You mentioned it's not at the right position, so you move the item a little bit. Does that mean your system can recognize the object in any position? Okay, you guys are the same designer and speaker. Okay. Do you understand what?
Recognize 3 points.
因为我们机械手不要垂直抓取那个物品的话，因为那个手臂的有一个部分太短，所以我们的工作范围很小，所以我们就只能在路径上先设置。
Okay. Well, my question is about case number 2. Can you show the case number 2? The video. Okay, so initially you move the blue to a new position. So does your camera tell you where the blue box is?
去学习，然后我们去拍我们这3个点有6个路径的6个情况。
I can understand. Is that your initial position 3? Okay. So you have to put everything in the right position.
我们当初是预测，因为我们假设是2个关系，所以会有2个正向线，然后我们假设是第3个是指如果关系掉落的话，可能会在这个位置，所以我们设定成3个。
Okay, so why can't you use different positions? Why do you have to focus on only 3 positions?
因为我们的相机有点不是那么专业，所以在技术上面的话，它会很容易，就量多的话，它很容易会错。
Okay, so what kind of machine learning did you use?
Teachable machine. Teachable machine.
Teachable machine. So you teach the teachable machine about the picture you took, and what's the output of your training?
Output. 我们就直接3个点。
So output is position 1, 2, or 3. I see. So based on that decision, you know where to take the robot, take the box. Okay, I see. Okay.
So I'm just curious about if all of the positions are already set, why do you need machine learning? So it says that you just recognize the color. So is the machine learning necessary, or you can use the other kind of methods to make it maybe easier?
Okay. Whoever can answer to this.
因为我想说，就是透过镜头，然后直接知道即时的物体状况，然后直接去辨识到，然后该走哪个方向。
Okay, so that is a real-time feedback. And how about that if, for example, if there is an object with maybe the other shape or the other, or we just put it at the other position, can it work? That can work, or
就是预设的，就那2个形状，然后3个。
yeah, but if that is a real-time feedback, it seems you can get the information like the robot arm is will get closer to the object or make the distance is smaller. If you get this kind of information, maybe you don't have to set maybe the fixed positions. Is that possible? You set a random position.
I think for machine learning, random position is harder, I guess,
Really?
because they need a lot more training. But from the earlier presentation, you realize you don't need machine learning. You can already recognize the position by some image processing to recognize the position of the object. But I think the limitation of your system is you are using 2D camera. So there's always missing information, missing the third dimension. For the other group, I think they are using 3. For the box picking, they have a 3D camera, so they know exact position. For the first group, I think they put the box on the table. So the Z coordinate is always the same. So similar to your case, you also put your box on the table. However, I think they take the picture straight from the top. You take the picture from the side. Did you take the picture from the side?
No.
Oh, from the top. Same, right? So if that's the case, you can easily recognize the x and y coordinate, and the z is always the same. It's on the table. So in that case, you can actually pick up anything if you work out image process. I know if you use machine learning, it will be more troublesome. Maybe the output can be the coordinate of the object. So you tell the computer, you show the computer 1,000 positions. Teach the computer what are the true coordinates. And then in the future, you put the object in a random position. Maybe the machine learning can tell you where it is. Then it's purely determined by machine learning, not by image processing. Maybe that would be one way, but I know it's challenging. But you can maybe elaborate more in the final report, or try to at least focus on something like that. Okay, thank you. Thanks. Let's move on to the next.
Hello everyone. So our team would like to present about the prototype for demonstrating the spin penetration test using robot arm fixed off with Robotics. So we have 4 people in this group, including me, and then I said Vera. And this is our concern. We have 6 parts. The first part is the background, of course, as I explained in the proposal. The goal for this final project is to demonstrate how robot arm help us to inject the needle into the skin. And then this is for the basic theory. We just use the basic theory like the transformation matrix, and then here is a table for the edge table for the robot. And then, yeah.
And for the computer feature we use in our project, we need to first calculate do the camera calibration. And first of all, this is the U and V is our when we capture a picture, and U and V is the pixel frame. And so we need to transfer the pixel frame into the camera coordinate system, XYZ, over here. So when we use the OpenCV camera calibration function to get the transformation matrix with this one and this one. This one is the intrinsic parameter matrix, and this one is the extrinsic parameter matrix.
And here we use a PDMS and Thursday to create our skin to simulate like this. And how about we calculate, we determine the joint angle or the desired position in the Cartesian coordinate and operation Peter called RBC in beta. And we just simulate the skin, and the upper part of the skin material use PDMS in one layer, and the lower cell skin we use 2 layers of the cell skin, and the right side of the figure is our end effector is like this, and we use 3D printing to make the end effector and set up our needle on it. And that is our environment. We can look at the first circle is is our end effector, and the second is that we simulate is our skin, and the third is the place that we set up the camera. And this is the robot that we use is RT60571. And since that we will focus on is our load, and in the end, the load is only 5 kg because we just simulate the needle, and the needle is even less than maybe 1 gram. So we will ignore the load here because the needle is now maybe just 1 gram. And here is our DHT board for our robot. We can check our A1, A2, and A3 is 30, 50, and 340 and 50. Yes, wait, 40. And D1, D4, and D6 is 375, 338, and AC 6.5. And next we can see this is our portrait of we are going to simulate. And in this project we will simulate we simulate the injection process, and we can see the start of our robot will stay at the home position. We will see in the next video. We utilize the camera for target localization to the needle injection site. And the second, we will use transform just like the last that we transfer the camera coordinate to the world coordinate. And the third, we use invert kinetic to compute joint angles for reaching the target position. After OA, we get the angle of all joint, and we can include the robot and calculate joint angles and execute the robot's arm and movement. And after we injection, and we will go back to the home position.
So before we use the robot, we need to make sure that in the calculation process and the real space have the same coordinate. Like as you can see in here, the XYZ in our simulation is the same as the actual position in the robot XYZ. Yeah. And then this is for the first position, and then this is the second position, also the same. The XYZ, all of them is both of them are the same. Yeah, and also for this one, yeah, they have the same XYZ. So we can make sure that for validating between the robot and the calculation is the same.
In this part, I'm going to introduce our camera calibration. So this is a video to present our camera calibration process. After fixing the camera in the place, we can use the chessboard to help us to calibration our camera. So I print a chessboard and put it with every angle place to capture the picture. And here I capture 20 images. After capture all of these images, it will save it in your files. And then I use the second program to calculate calibration the camera, and I will get all the transformation matches from pixel frame to the camera coordinate system. And then after calibration our camera, I will do the application. And here is a video of the process. First, I use ROI to choose the region that I want it to detect. And then it will give us the detailed results. And we use these points into our MATLAB code. And in our MATLAB code, first of all, I will use the
transformation matches that I get from the camera calibration, and then transfer the pixel to the camera coordinate system. Here is our resource. Here is from our pixel frame to our camera coordinate system. And then I input it into our camera coordinate system, transfer into robot coordinate system code. After I input the position the camera coordinate system, and then we use robot to move to the point. And then we can get the robot coordinate system that is at that point. And then we can put it into our manual code to combine these two kinds of the place, the coordinates, and we can make the transformation matches from camera to the robot coordinate system. And now, when we run this code, we will get the transformation matrix and the target point in the robot coordinate system. And then we put this resource into the inverse dynamics to calculate the robot position with the target point. And the next process is to move the robot to the target point. And from our experience, we can see that our camera detection has some errors between the robot. The robot here is the actual position of the target, and the kinetic calculation is from the simulation that you do. So you can see that the error between robot and kinetic calculation is a little bit smaller than our camera. And I think the reason why we have big errors between the camera is because that our camera is used the 2D camera, and we just use one position to capture it. So the depth displacement has a bigger displacement between the camera and robot. So if we want to increase the detection, we need to use two cameras at a different position to calculate the one target.
This is our conclusion. Our robot demonstrates it's a middle intuitive scheme we made with PDNS and skill scheme. But we encountered some limitations during the simulation, just like disability when the robot moving, positioning, direction, and they are not very accurate between calculation and testing. And the camera we use is a 2D camera. In this final report. So, but it can only capture X and Y. So we discussed use 2D camera or a 3D camera to capture the relative position of our skin and the robot to minimize quantity of error and make a relative position more accurate in the future. And this is our reference. Okay, thank you.
Okay, so I know camera and robot always has position error. That's definitely some issue to be resolved. So maybe in your final week, we can propose to solve this kind of issue. But I think that's not the main issue. The issue is you made a skin prototype and you want to show how you can insert the needle. So usually the needle is inserted in an angle, not straight, right? So why did you consider to, perpendicularly insert the needle?
Because in our event, because I think when we inject the needle, it's just we're not getting a blood or something. If we were just like 疫苗，就是一些就是它是可以直接植得进去的，不是为了要抽血或干嘛。
Muscle injection.
Yes. It means we inject like a muscle injection. We just need to go into in straight and come out.
It's an easier way to complete a project. I see. So technically, the complexity of the project is not very high. You just made artificial skin. You made an effector with a needle, and you match the simulation and the experiment, and use camera to identify the position and then insert. So I think the complexity is not as complex as RT. So maybe at the final week you can think about what you can look into. Because I think this is a really good topic. Maybe you can try the vein insertion. Yeah, maybe. Okay.
Well, it's just a suggestion that, or maybe this other, that is because as we know, the patients they have to get the injection. Generally they are afraid of the needle, and sometimes maybe they incline forward, backwards to they want to maybe have a lower fine or something like that. So can your assistant deal with this kind of situation? I know it sounds like a horror movie, but is it possible to deal with this kind of patient?
Okay, sorry, can you repeat again the situation? So you mean that
Sometimes the patient moves.
the patient moving?
Yeah.
For now, this current system, I don't think we can, how to say, our system can do it.
Yeah, you cannot handle this kind of movement, but
Yeah, that's true.
I guess that you can at least propose what to do. What do you think how we can do that?
So maybe we can use the identification to capture
Like
real
a
time.
moving object tracking?
Yes.
Maybe. Maybe you can do it. Move the needle. Maybe.
That is why I think that because if you want to slightly extend this project, I think that it is one of the opportunity to do something more than spiritual.
Okay, thank you. Next. So Tahir dropped.
Yes.
Okay.
Good morning, everyone. This is our robotics final presentation. My name is Cindy, and it is Daniel and Alice. And our topic is kinematic analysis and simulation versus Lex robots. As our proposals few weeks ago, we are going to design the 6 Lex robots. And after our proposals and the suggestions from the professors, we add 1 degree of freedoms from the proposal design. And this is the components of our robots. We use 12 server models on the robots. And on the left-hand side is our legs, and we put 2 components as the bits for the legs and use Arduino to control. And for moving, first of all, we have 2 types of legs, such as white and black. And the kinematic can show on the left-hand side, the pics on the left-hand side. And the timeline shows on the table. And when the switch in between 2 bits, there will be a time to step on them at the same time, and which can reduce the occurrence of vibrations. And here's the simulators of our Arduino. And this is the robots that we have made. It can work like the video shows on this slide.
So when we come to the design, our system is a 12 degree of freedom robot with 2 degrees of freedom on each leg. So we have 1 revolving joint here. We have totally 4 revolving joints and 1 translating leg. So we try to make some modification on the design. Usually the conventional design is an 18 degree of freedom with 3 revolving joints on each leg. So we call this the coxa. This is the femur, and this is a target. So we make the coxa and the femur as in 1 link, as you can see here. This is 1 link, and we make the tibia part as a separate link.
So after assigning some proper axes and geometries on the leg, we formulated the DH table, and then we get the transformation matrix for the entire leg. And as we can see, the leg moves A1 cos theta 1 in the x direction, A1 sin theta in the y, and it moves in the z direction with L value. So we have also done the Jacobian analysis to calculate the velocity and torque requirements using the proper angular variations. So theta 1 usually represents the femur, and this is the femur and coccyx leg. So this will tell us theta 1, and this will give us theta 2. Okay. So after we done the kinematic analysis, we go to Adam's simulation to check what the behavior of the robot will look like. So initially we assign the material. We use aluminum for all the components, and then we set the connection. We have a total of 24 revolving joints, 6 prismatic joints, and 1 fixed joint, which is the ground that the robot will work on. And after that, we assign contacts from the tip to the ground. And then we created the required motions. Okay? So the motion will execute using a step function. So we have the step function has 4 variables. Okay? So we have the initial time, we have the initial position, we have the initial time, initial position, final time, and final position. So this step will tell us how theta 1 rotates. Okay? So initially theta 1 will have at 0 degree, and within 5 minutes it will reach 30 degrees. That means within 1 second it will rotate 6 degrees. So simultaneously the prismatic joint will also move the leg upwards, because as it rotates, it cannot drag the tip on the floor. So it will again it will have an initial time of at 0 seconds. It will be at 0 degrees, and to clear the ground about 12 millimeters, it will rotate 68 degrees. Okay? And then it will rotate, it will come back again and rotate the arm after within 5 seconds. It will rotate it with opposite 30 degrees. Okay. Then this is the step function for one leg. So as you can see from our model, we have 6 legs. The white ones will move at the same time, and the black ones will move at the same time. So they are moving randomly. So as the rotation finishes, it has to, at the 15-second mark, it has to move the arm, the prismatic joint arm to the upward position, so that the other leg can rotate without dragging the previous one. So you can see here that within 0.1 seconds, the tip of the leg, or this prismatic, will rotate minus 68 in the opposite direction so that it can continue the rotation. So after setting up these step functions, we run the simulation for 20 seconds. So this will be, so I will run the simulation 2 times. So now you can focus on the theta one first. So it will move randomly. So the 3 will move 1 time, and the other 3 will move after 5 seconds. So now focus here. So you can see the jolt of the prismatic is within 0.1 seconds. So it can rotate with the randomly with the other leg. So after running this simulation, you get some results on the joint forces and torques. So in our design, this is joint 1, this is joint 2, this is joint 10, and this one is joint 4. So you can see from the simulation we have the fx, the force in the x, y, and z direction, and we have the torque in the x, y, and z direction for each joint. This is for joint 1. So we can see it has a maximum value of about 0.15 newtons and 0.51 Newton meters, and for the joint 2. So you can see this is the time variation within 5 seconds. So after starting the R, it will gradually increase to a maximum value and then fall to the its minimum value. So these are the torque and force requirements that should be applied on each joint. So this will tell us that we can select the specific motor for this joint 4 and joint 8. So we can have, let's say, for joint 4, yeah, this is joint 4. We will at least we have a motor with 14 Newton millimeters of torque to move the entire leg. And for the joint 10 also, we have the torque and force plots. And after that, we get the velocity and acceleration profile of the leg. So this will tell us the entire leg, the velocity and acceleration of the entire leg. So Cm means at the center of mass. So from the design, it's about the center of mass is about here. So this will tell us the acceleration and velocity of this point. Okay. And for the tip, that means this part, it will also have their own corresponding acceleration and velocities. So we can see a maximum velocity of about 15 millimeters per second for this point, and we have about the same with for the tip also. So this is the result that we get from the Adams simulation. So we can now see the demonstration.
less sleeping. Walk on the top. Oh, it's too.
Yep.
Too wide. Maybe the other one would be rotate 90 degrees. No, I can. Well, it's okay. That's it? Okay.
Yeah.
So, it's pretty good that you truly make one robot with 6 legs. So, yeah, like you mentioned, the slippage is an issue. Maybe in the future, later on you can try to attach something to avoid slippage and see if that can make sure it moves with a faster speed. But I noticed there's an issue. When you have legs moving forward, you basically rotate like this, right? So when you do this, the distance between 2 feet is narrower. And when you recover, you actually become a wider position. So that kind of movement will cause slippage as well, right? So your design is meant to slip on the floor, right? I guess to avoid that, you need even greater degree of freedom. But at least you can try to analyze the situation about slippage. Okay. I guess that's the main issue. The rest should be okay.
At first, I think the topic is interesting, and also it's great to see that you complete that with the full process, including the analysis for the test planning, the simulation, and also the prototype. So I think it's a great work in this course. And just a few questions, like I think you showed the velocity, maybe that is a simulation velocity curve. Yeah, like this. For the middle figure, that the red line, so the red line is the velocity at which point or which link?
This one?
Yes.
This is the velocity at x level.
Yeah, but at which link?
The tip, this one.
Okay. So how do you think about the curve? Because it seems to move downward and slightly upward again. So what kind of motion methods to change this kind of performance?
So your question is how can we
Yes,
change?
that is what happened at maybe the horizontal line, that is the time. So what happened at the 5th second?
So at 5th second it will stop.
Yeah.
And it will rotate 30 degrees, and it will attach itself to the ground. And within that brief moment, it will rotate again.
Really, but I think for this type of situation, maybe for it goes downward, the velocity it should be negative. It not just decrease. It must be negative. And then when it moves upward, it should be positive. So could you please check the curve? Maybe they just maybe you take something wrong setting, or I think you have to explain what happened at that moment, because every curve with this, especially the bottom one, I think you have to explain what happened at that second.
So this one will tell us within the 0.1 second,
Yeah.
it will accelerate from 68 to 0 degrees within 0.1 seconds.
But why the value is so large?
See, it will push it to the ground fast within 0.1 seconds.
to sense this kind of motion?
Because you see that as it rotates, it has to come to the tip has to connect to the ground within that time, because it has to touch the ground within that short period of time, so that the robot can rotate the entire assembly forward.
But what will happen if you make this velocity slower? Just because it happens only when you put down the rack.
So this time will go down, and then to drag the entire robot forward.
But if it's more, I think the motion is close to perpendicular to the table. So if you need the force to pull it forward, I think maybe you have to make a rotation, maybe to put down your head, maybe backward with an angle that to generate the force in this direction. Okay. However, I think it's still a good word.
Thank you. So the other person dropped?
Yes.
Okay.
Money or growth? Only Henry. No.
Those are money.
Yes, money or growth.
Okay.
Oh. Okay, good morning everyone. So today, my name is Edmund Giroto and my friend Henry will present about our project ARM robot solver with Arduino. Yeah, it's a bit different with our proposal before because, well, we have tried to use hybrid robot but we cannot make it to solve our problem, and then we think how about we create our ARM robot to solve what we want. So the idea is we want to create an ARM robot with power with Arduino to solve simple case. So it's just like the orange ball go to the orange cup, and then red cup, and red ball to the red cup, and then the purple ball to the purple cup. So the idea like this. So we create the robot, ARM robot with 5 joints, which has power with Arduino, and we will use ping pong ball as moving object to put that into the cup, like this one. So in this, to making this robot, we will need Arduino Uno, R3, and we will use Arduino Servo Shield for making that easy to use this servo, and then we use vacuum section to moving the ball, and then we will need 2 servo micro SG90, and then MG9, which is MG9 is have more maximum load, so we will put that in this position in the bottom, and in the first joint, second joint, and the third joint. And then this is how it's look. So in here, the first link is 55 millimeter, and then second 90. The third one is 30. Fourth one is 80 and 60 millimeter. And then for the center one, we assume that as 0 because after we calculate, it's just center point, so it's just unnecessary. So to find our position, so we need first to find forward kinematic, and then this is the H parameter of our robot, and then we get the data in here without the n factor. The point is 110, 0 and 145, and with the n factor 170.0.145. Well, to do the experiment setup, so we will use laptop here with Arduino Uno, and then this is the Arduino, and then with battery, and then this is the suction pump. And then the target is we want to move between this object with several sequence. Depends on what we want to do. Yeah. So what next? Yeah. To make it work, so we plan several positions. This is the angle of every servo motor move. So to put the ball here, we just create several moves to make it more easier. So yeah. Well, I hope I forgot what the word here. Well, I hope the robot will work well because it's a bit sensitive because we made it with cardboard because we want to find. Yeah, I'm sorry, it's not really. Yeah, it will be something like that, and then move the ball to the point we want, something like that. So the solver, yeah, but sometimes. If the problem is when we move the robot, we need the position will be different, so it will be affect the balance of the robot. So we will see the video later how it works well. So this is we want. So the first case we will just move from to the front of the ball like this one. So this is how it perfect position we want. Like this. Yeah. And the last one. And then the next one, we change our pattern, so it will be moved like this one. Get a bit faster. Yeah, like this. So the ball will be started with the vacuum, turned on by this one, and then it will be moved depend on the coordinate, and then it will be put the ball on the cup like that. Yeah, this is the last pattern we made. So as a conclusion, yeah, we can get the Arduino capable for create the arm robot, and then the arm robot can solve problem, but we still create the coding manually. So actually we have tried something, but we still not make that in time, so we cannot show it in this presentation. And then with Arduino we only can do the limited system. And then this is our reference. So what's next? To make the system automatically, we think that how if we combine Python with Arduino. So to connect Python and Arduino, we will need those inside that. Yeah. So this is what our future plan later. Thank you.
Okay. So actually, in the lab, there's already physical robots. I'm curious why you want to build one on your own.
Yeah, the problem is we don't know how to control the robot, so we want to make that move automatically. In hybrid robot in our lab is only like only PTP, so we just put the number and it only moves one time. It cannot move like several sequences like that. And I have asked some senior how to send the data. They always say you don't know, and I tried to learn some things and I didn't make it. So I think how if I make new robot? So because the limited of time, so I plan to make this. That's why.
It's when you manually build something like this, you will spend a lot of effort on making it accurate, but it's never gonna be accurate.
That's true.
And you see how uncertain it is.
Yeah.
So it's not much you can improve because none of the parts are metal. If you choose metal plates, maybe it will be better. Yeah, but when you use metal plates, your motor won't be powerful enough. And there are several resources in that.
Yeah.
I hope you make good use of it. Okay. Anyway, try to do something on the final report.
Yeah. Thank you.
Well, I have to say the task is not so difficult, but because you made your own robot from zero, so it makes this project very impressive. So this is just some suggestion that I think because you make both the joint control by yourself, obviously you don't have the existing the control. So I think maybe in your final report you can also show your kinematics, like the forward or inverse kinematics that you set a position, and then how do you control which angle you turn the loop in the specific angle position. Yeah. Okay. I have to say, as a purpose, we set this project, and we want to learn how to use the truly robot.
Yeah.
However, I think that is the other way, and I have to say, at least you try that, and I think you also learn something from.
Yeah, that's true. I also understand much about inverse and forward when I made this robot.
Okay, so that is all my question.
Okay, thank you. The next final two teams.
Hello everyone, my name is Mongzhen Li and she is Li Xiao.
and she is Yujun Huang. Our final project topic is method of robotic center point calibration. And this page is our outline. First is introduction, second is methodology, and third is verification method and result, and fourth is conclusions, and the fifth is future extension, and next one is reference. And this page is introduction. The precision and accuracy of a robotic arm are crucial for various applications, and the calibration of the tool center point is a key step in ensuring the accurate execution of tasks. In this study, we used two methods for calibrating the TCP of a robotic arm. One is the numerical method, and the other is geometric method. And additionally, we explored the validation process using different tools such as screwdrivers and pen tips. The reason for using these two tools is that they both feature shape and points, and they will providing better accuracy during the calibration process. And our experimental objective is to teach the robotic arm at the same point position using 3 different orientations, and as depicted in the image above. And then we will compare the XYZ coordinates calculated by the Epson software with the result obtained by inputting numerical values into our program. And we aim to validate whether our program outcomes align with the calculation performed by the Epson software. And then we will reuse other verification methods to ensure accuracy and consistency of the results. And because we are not sure about the specification of the tool, so we culturally secure with tech.
Hi, I'm Rit, and I'm gonna show you how we reach our goals. So, as previous proposal, we mentioned that we came up with 2 types of method, and this one is the numerical method, and we discovered that the calculation of TCP should be could be displayed like this. And in past 2 weeks, I turned that into code, and from the XYZ UVW of each posture, I'm going to find out the XYZ of the tool. But something went weird at this point, because some data and some results are correct, but the others went wrong, like this one. The expected outcome should be 31.5, and the unit is millimeter, but the outcome is far away from that. But I was really confused at this moment, because if I use the same data, calculated it with the online matrix calculator, the answer always correct. But if I use it, I tried it on no matter Python, C, or MATLAB, the answer will go wrong. So at first I thought there was something wrong with my code, but after that I find out that in the calculation we have to, one step is we have to obtain the inverse matrix of matrix A. But sometimes the determinant of matrix A is quite close to 0, so for programming, they consider it as a singular matrix, so it never get the right answer, and this is the reason why my code went wrong. And the bad news is I didn't solve this problem in past 2 weeks, but the good news is we have good progress in next method. So let's move to the next method. And brief review of the geometry method. So we have 3 posters, and they're a vector pointing at the same point, and 3 origin points form a triangle. On this triangle, there's a point equidistant to each origin point, and through these points and perpendicular with the triangle, there will be a line, and our target TCP will lie somewhere on this line. So at first, I do it in only pure math. So I assume that I already know the tool and slightly should be 0, 0, 100, and the 3 postures are pointing at 0, 0, 0 in vertical coordinates, so that we can obtain 3 homogeneous transform matrix. And after that, just forget that the assumption and started to find the target TCP by the 3 homogeneous transfer matrix. And so basically the point that is equidistant to 3 origins is the circumcenter of the triangle. So I define 2 vectors perpendicular with line AB and line AC, and also find the midpoint of line AB and line AC. And by these 2 points, we can get the parametric equation of lines. And so by allowing us to get the circumcenter in matrix form. And after that, I cross vector AC with vector AB to find this yellow vector. With this vector and the circumcenter, we can find another parametric equation of line. And after that, I just searching it from the end to the top and trying to find the lowest position of the paragraph is the arrow of each vector from their origin to that line. So the minimum of the value is the value that we want. And in this program, I set a variable value called step, and it represents the resolution we found the minimum point. And here is the result. I set the step as 0.00001. And as we can see that we expect the outcome should be 0, 0, 100 and 80, 90, 30. And as we can see, the deviation is acceptable, it's quite small, and so I move into the next stage. So I have done a simulation, and so in simulation I made the 6 axes. I enhanced the length of 6 axes, just pretend they have an HR tool, and I made them to touch the same points. As you can see, the gray spot there, and the outcome still looks good, and my code can find the new TCP. So after pure math and simulation, and this time for real robot, right? But if I just remember that our goal is like I just randomly put something and randomly just type something on the robot, and the robot should know the new TCP, right? But if I just do that, we cannot see the arrow numerically. So I came up with another thought that the robot we use is Epsos robot, and Epsos robots actually have a function that you can assume it has an invisible tool. So I set several sets of the tool and trying to derive back if our tool as close as to the assumption. And I did it quite a lot of times, and I picked 6 sets of it. And first 2 sets, we can see the deviation is quite small, which was good. But in these 2 sets, the deviation of x of data set 4.066 is not as small as I expected, but still acceptable. And the next one, the set 5, the x, still the x, the deviation is 0.104. It's quite big, but if we just compare it with expected outcome with real outcome, we will say it might very close, but just a little bit of error. So after these 3 experiments, I know that my code should be functional. So later, my partner will continue to introduce how we verify our results on the real robots.
And this is our first verification method. And we set a screwdriver and hex key as tool for calibrating TCP. And this video demonstrates the calibration process using a hex key. And we calculate the calibrate data and compare the data calculated by Epson itself. And you can see the robotic arm calibrating the same position using different orientation. And the part involves testing where the robotic arm rotates UV-W and goes to the same point after calibration. And the angles are calculated by Epson itself. And you can see that the rotation in U is accurate. The rotation in V and W is do not align at the same position. And then we using the data we calculate and applying it to the arm. You can see that the rotation in UVW at the same point. And this page shows the newly defined PCB data after calibrating with a screwdriver. And on the left side of the image, you can observe that the Z value in the XYZ coordinate calculated by Epson itself is significantly large. It's about 60,000. And on the left and on the right image, it seems to be display the data generated using our calculation. And then you can see that the XYZ values are more in line with the actual compilation result. And this page represents the calibration performed using a X key as a tool. And then you can see that the Z value, both sides are different. This is second verification method. And the second verification method involves calibrating using a red pen as the tool and repeatedly drawing zigzags. The image below shows the robotic arm drawing zigzags on paper using the red pen. And this video demonstrates the calibration using a red pen as a tool, followed by repeatedly drawing zigzag 10 times. And you can see that the red pen tip consistently lands precisely on the same path. And the third validation method involves separately calibrating with a screwdriver and red pen. First, all points are calibrated using a screwdriver, and then the red pen is used to repeatedly traverse the same point outside the action text. This video demonstrates the calibration using a screwdriver as a tool. After calibration, a path simulation is conducted approximately After calibration, the path simulation is conducted approximately 10 centimeters above the action paper to ensure smooth movement of the red pen during drawing. And next video demonstrates the calibration using a red pen as a tool. And then it follows the path of the previous calibration points with a screwdriver. In the end, you can see it. In the end, you can see that the action text drawing is quite accurate, but not complete. And possible reason for this could be that the working platform is not entirely flat, or it might be due to the phenomenon where the red pen tip retracts slightly on contact with an object, causing a minimal discrepancy with the pen.
We divide the conversion into a two part, and the first part is zigzag. And after repeat movement of the robotic arm, the precision accuracy has not been lost, and there is no intuitive error. And the next is the robot arm is positioned correctly. However, the latter didn't touch the surface of the paper when the pen was drawing a line, such as letter E and N. We discussed that the screwdriver may not have actually touched the surface of the paper when calibrating the point, or the lead Z-axis was not adjusted properly when the pen was drawing a line, which caused the pen tip to sink in. However, after adjusting the height, the pen was able to draw the line along the predefined path smoothly. And finally is future development. Currently, the program is written in such a way that each piece of data is compared with the previous one to find a min-max value. This is a very slow way to run the program. So to optimize the program, we can start from this part. And the next is considering the rotation of the tool. The current algorithm doesn't take into account the orientation of the tool. But the orientation of some tool is different from the arm, like the welding head. So we can think about this more advanced way. Thank you.
Can you go to page 17? I think this is where you find the solution.
Yes.
I'm not sure what does the figure represent. You didn't show the label for axes.
So in this step, we are searching through the entire line to see if any
Where is the line?
the line 就是垂直的。
Perpendicular.
Perpendicular to the triangle and
Oh.
Yeah.
So what is the y-axis? What is y?
Y-axis is the arrow
Arrow of what?
of
Plug in the equation.
plugging.
When you plug in some equation and check the error.
Yeah, I plug.
Do you have an equation before this? Do you have any math equation?
equation 就是the vector from each origin point
Okay.
to that line
Okay.
on each coordinate should be the same. 就是
The vector from A, B, C to that common point on the straight line.
Yeah, should be
The
the same.
vector should be the same.
The dance.
Or it should stay on the same plane, or?
No, it's not stay on the same plane because the line is this one is this point is circumcenter.
Will you do better if you use Chinese?
我试试看，就是因为它的那个我们那什么外接圆圆心，对，所以它理论上它到每一个坐标原点它是等长的，所以每一个坐标原点只到那一条垂直的线。
The length of the vector needs to be the same.
全部都是等长的，但是
Why?
全部它一定是等长，因为这是它的外接圆圆心啊，所以一定是等长的。就是为了找这个外接。
Okay. So same radius. Okay.
same radius， 然后但是这个 vector 在coordinate A 上面 respect to coordinate A 的数值一定跟 B、C 不一样，对吧？但是我们要找到那个点，假如说它刚好是1、2、3，那它也要刚好是1、2、3，它也要刚好是1、2、3。因为每一个的 orientation 不一样。对。
I'm just curious why you can make all of the vector become the same.
就是在那条线上一定会有一个这么一个点。
So you adjust the coordinate for each point.
没有我就是让程式去跑跑的是直线从这个直线跑到另外一端的直线，每一个点去测，就是。
Okay. What did you calculate?
What
did you calculate for your 每个都去测？
好，就是我去因为我需要他们一模一样，所以我去将它们互相相减，然后相减的 error 去 square。
What minus what?
X Y
XYZ coordinate of A minus XYZ
coordinate of B. And I did it.
But they are not the same point.
Not the same point. That's not what it said.
Why are they the same point? They are different points.
Same point. Same point.
不同点啊？为什么你说它是相同的？
相同的点。
那讲台语的。
我们现在为什么？我们可以明白它的像是一个外接圆心，所以它的3条线很长。但是为什么可以说这3个向量都可以找到一个地方，让这3个向量是一样的？对，为什么会一样？
对啊。
你说这3个向量到最后会找到一个点，让它这个点出来到这3个向量会一样吗？
不是，那个向量是原点到找到的
原点在哪？
原点是这3个。
OK， 3个坐标系。
3个坐标系的原点。
那这3个坐标系是同向。
不同向就是。
那坐标系的
的，
听懂吗？它是三个。
就是最一开始是，就是你可以看到后面的淡化的就是那个
OK
3个 posture 嘛，所以理论上他们会接触到同一个点，但是他们的 orientation 不一样。然后我们需要找到就是这个 vector 的话要有2个 constraint， 第一个 constraint 是这个点距离3个 orientation 的原点必须要是正常的。然后第二个呢是那个 vector 在 A frame 上面的值跟 B frame 上面的值、C frame 上面的值要一模一样，那这样我们就可以找到。那我们刚刚的那个表格就是这样，就是找到外接圆圆心，然后找到一个 perpendicular， 然后就是沿着这个一直找，它会有很多组，对，然后那个
那还是不知道你算什么。
这个就是因为我想要找到它一模一样，所以
对你的那个 y 轴的值到底
就是那 y 轴的值是就是
什么的 difference， 什么的误差，你算的是
这3个那个
3个互相相减嘛？
对
，A 的减 B 的再减 C 的，还是
A 的减 B 的，B 的减 C 的，C 的减 B 的，之后他们是
那有取平方吗？
有 square， 所以它才是一个很漂亮的。
这就是一个 square error 嘛，对不对？
对 square error， 对。
那就减出来了。
哦，不好意思。对，然后
OK， 对，这个要 you have to precisely define what you do. It's a good work, but you need to precisely define it.
I suggest that maybe you can show the equation you use to show what is the result and what is the label for x and y.
Okay, so for this kind of problem, if you learn from a course or learn from a paper or from a textbook, usually there is a very clear figure with symbols, and usually there are equations. You need to think more about how to write down those mathematical equations so we can understand easily. I know you know what you are doing, but you didn't describe in a mathematical way. Okay, I think this is a optimization process.
Yes.
So you don't need to check everywhere. You don't need to, because there's a approach to find the meaning. Taking an optimization course. Okay. So in your example, did you use the method right here?
Yes.
In the example?
Example, you mean
all the videos.
Yes.
So you use the method.
So actually, it kind of worked because at first I want to compare my result with Epson's result.
Okay.
But as you can see here,
so your result is less accurate than Epson's result. Epson is better. Yours is better than Epson.
Yes. 就是如果它旋转的话，理论上它的那个末端点会定在同一个点，不管它怎么旋转。但是 Epson 的呢，那是这边吗？它就是它绕着U 旋转的时候是对的，但是 VW 却这样子跑掉了。然后
Maybe you did it wrong.
I just used the
standard procedure in Epson, right?
它是一个方选，就是叫你摆3个点，然后它就自动算。然后我接下来算的呢，也是跟它拿一模一样的数据。对。然后后面这个就是
我用中文好了。
哦，对不起。
说不定你做错了。
好。
对啊，因为 Epson 它这个很有名的系统啊，所以你怎么知道它是错的？
可是我是按照那个因为我不是说我们另外一堂课有用到这个方选，然后我很好奇怎么完成，然后我是按照那堂课的去。
但是人家敢这样卖，应该不会错的，所以有可能是操作的时候有问题。你怎么知道你操作的是对的？
可以问一下的，是 就是你有上那堂课的嘛？就是你用这个功能的时候，就是真的啦，就是用10次，然后大概只有2次是对的，然后我们这一天不管怎么测都测不到对。
OK， 这个有时候是不知道是操作问题还是 whatever， 理论上commercial 东西不会错，理论上不会错，他们在做这个是很有。
不过有可能我们那时候有跟另外一个老师就是问说为什么这个问题，他是说这个机子是10几年前的东西，说不定它的那个更新没有更新完全，所以我们后面才去想其他的，先用一样的。
你的方法是对。
对对对。
Okay. You chose 3 configurations.
Yes.
Maybe you can try a 4th one.
Yes.
Or a 5th one. Right? But when you do that, are you going to find a true solution? I'm curious about more configuration. Maybe you can try it.
I did a survey and I find that LED used for configuration to find the orientation and the position, but I didn't find any paper written.
We don't need a paper. By math, maybe you can think about how this can be done with more configuration. Is more configurations going to be better or worse? Yeah, we can think about this. And sometimes if you have more configurations, because multiple configuration, they don't overlap at the same point. So sometimes, I'm not sure, because you didn't show the map, I cannot think clearly about the problem, but I guess when you have more configuration, there will be some issues of the number of information larger than number of unknowns. Remember when I taught you guys about hand-eye calibration? There is a number of unknowns and there is a number of equations. Usually we need same amount of numbers, but sometimes we can prepare more data. When the data amount is larger than your unknown, sometimes you will have approximation. So like I talked about least square approximation. 最小平方法. So maybe if you have more configuration at the end, you are doing least square approximation. Actually, least square approximation is a method about minimizing square error. So I think you are already doing minimizing square error. Yeah. Okay, anyway, I think it's pretty good.
My next question is, you're dealing with the issue about collaboration. What you set your tool by that?
Because we want to show, I put it randomly. I really don't know the really XYZ. But if we in real 真的实际去运用的话，就是会真的不清楚。我们就是想要展示，我们真的是完全不知道它的那个工具的 XYZ 到底是多少，它随便这样贴也可以，这样贴也可以找到。对。
But okay, here you provide 2 examples. I think this figure that you show, it is a good example to show your accuracy because it can be repeat of the past. But for this example, maybe not so good because obviously there is the error is about 1 millimeter. I think the problem is because you change the tool. Originally you use the screwdriver and then you change the red pen. I think that is the error that causes the error. So maybe this example is not so good to, especially when you want to show the result of collaboration. Okay, so it's just some suggestion, and I think that maybe you can make some improvement for the right.
Okay, thank you. Finally, the final group.
Hello everyone. Today we will be presentation for painting robots. And here is our introduction, flowcharts, process, and the calculation, and the future planning. Introduction. Painting is an essential component of the automotive industry with an annual production demand exceeding 50 million vehicle and robot arm for painting test of the faster and high quality results. In this project, we utilize camera for image recognition and face generation through Python program. This enables the robots to autonomously detect the painting area's position and follow the current painting pace.
Okay, I will explain about the flowchart. Firstly, we put the material which will be painted to the above the working table, and then we install the camera to capture the working plan. Then the data from camera will transfer to computer operation. In this computer operation work, firstly, we identify the area which will be which for painting by image processing. After we get the area, we generate the painting pad. Use a Python code program. Painting pad is like a painting pattern. After we get the painting pad position, we simulate the robot using the SAR sim to see the motion and the trace of painting pad. After that, we make the pad decision from the painting pad from the robot simulation. If we agree about the painting pad, we will use the painting pad for the robot operation in experiment. If we still not satisfied, we still can regenerate the painting pad. Example, like increase the density of painting pad. Then to go to the experiment work, this is the high beam robot operation control. For the input, we use the painting pad position from the computer operation. Then the output is I command the robot to the painting text. Okay, next one. This one is experiment arm setup. Firstly, this is the robot. We use 6 degree of freedom of hybrid robot. This is with the A4 paper. This one is the material will be painting. Then this one is workable. We use a real brush tool mounted on the end effector. Then this one paint chamber contain the real oil paint. In the brush tool, the robot will sink the brush tool to the paint chamber during the painting operation.
Okay, so here's what we did. So we took some tests. We took a piece of A4 size
A4 size piece of white paper and then a random path to test if the robotic arm could implement the movement according to the path we wanted. So you like this one. And we also try to test it with the simulation before operating it with the real robotic arm. And after it's success, like the image, then to achieve our idea, first we wrote a program in Python that will automatically generate the painting path according to the size of the range I give it, like that. And the range I gave was 300 times 210 millimeter, which is about the A4 size. And then we changed the predefined range to the paper range recognized by the image, which is 253 times 147 millimeter. Then the program will calculate the range to automatically generate the painting path. And we also purposely shift the range of the painting path to make sure that the generated path are all on the paper. And next we have made a few simplification to the path so that the robotic arm doesn't have to move too frequently. And we have setting up only a few waypoints. And because there is an error between our image recognition and reality, so we have rescaled the range using Excel to calculate the new waypoints and program them into the robotic arm. And here is we use the simulation about the two paths, and it will follow our path, and then the second time it runs, it will make the action of the painting by painting the path in two modes, a sawtooth mode and a square wave. And in case 2, the robot arm will also follow the calculated path, and it will redip the paint in the middle of the path and then complete the rest of the path. And here's the video we implement.
Okay, and this is our video about our case 1. And so we will reply the paint. And this is case 2. It's also during the process is real glass. And this is final results. Results is here and it's generation.
Okay, for the conclusion, finally, our robot and its planning motion strategy have successfully demonstrated the feasibility and effectiveness of robot painting task. It has proven for the alignment of the painting path between the simulation and experiment. Then, the integration of the image recognition by camera and pet painting generation by pattern base is a great combination, resulting in a precise and consistent painting result. There is a strict difference in a path alignment between experiment and simulation. It could be due to the work paper is not stable. Then we have a future planning. For our future planning, we want my robot is applicable to more complex painting. For example, for the logo or livery painting. Please see this our recent project. Our robot has successfully to painting in this rectangle area by one color. My future planning is our robot can do this logo painting by multicolor. So in the future planning, we need to develop more complex painting path planning algorithm. For example, not only zigzag as my recent project, our recent project. Then we need to develop the motion planning for tool remove and pick, for brush tool, for multicolor purpose. So only one robot we can our robot can applicable for more than one color. Then we need to mount the camera on the robot elevator. The purpose is to improve the mobility and get the recognizing information to the working plan. Okay, thank you.
So can you move to one of the videos that you truly do? Yeah, this one. It seems like you are moving the robot pretty slow, right? Pretty slowly. Because everyone in the back is moving so fast.
Yeah.
So why do you choose to move the robot so slowly?
And actually, we have originally tried to use the code to control the robot by automatically, but after we type the code in the robot gun to operate it, and it goes very strange movements. So after sometimes tried, and we try to use another way to control it by point to point to go to the point and when I calculate it. So that's why it's so slow.
I think this part can be improved.
Yes.
Maybe some of the coding or some of the setting is not appropriate. I would recommend you to study further, because this is quite standard robot motion, and it's good that you automatically generate some kind of pattern. And there are once you have a pattern, you can easily get point information from the pattern you create. And the next, what you need to do is to move along those points.
Okay.
And you should be able to control the robot motion with a more appropriate speed.
Yes.
And this shouldn't be too difficult.
Okay. Thank you, Professor.
Okay. My question is, could you please go back to, I think one of the slides that you showed, maybe previous one? Previous one.
Yes.
I think there is one page you show that you have that is as a task planning, you have a line and you put many points at that line. Yeah,
This one?
So, I'm going to, I'm just curious about how about this, why you have to put so many points? What's different between because there are so many positions you have to reach?
Yes.
But what's different between if you just put fewer points?
Yeah, so we found that function too, and then later we simplify the distance between x and y, and let it just become just a 3 point waypoint. So that, yeah, that's the.
So the point is for the velocity control or why?
Yeah, we can adjust the.
That is not my point. That is how many points that is okay. But I just wondering what's different.
Sorry, Professor. Actually, in my case, I ignore this point, Professor. I only
use this top to top point reference. I ignore this.
Okay. So how about this slide? Okay. So the other question is about, because you mentioned that you use the image recognition for the size of paper.
Yes.
And then could your system also recognize the shape of the black line?
That we want to do this in our future. We're going to improve it. But for now, our program cannot recognize the line, not yet.
Why?
It could, but we can. And maybe we do some modify about our program, and it could recognize the line. Yes.
Okay, thank you.
Thank you.
Okay. So, I think every one of you did pretty good in the final project. To be honest, many of your performance was greater than my expectation. So I'm very happy about what you have done for the course. Actually, this is a pretty good training for your future research and publication. The way you present on the stage is just like how you present in an international conference, or how you can defend yourself for your thesis or dissertation. I know for Taiwanese, language sometimes is very difficult, but you never know whether you need to travel outside of Taiwan for an important meeting in the future. So I would say try to force yourself to use English, because English right now is still the most common and well-used language for the entire world. Okay, so yeah, what else you want to say? Okay. Any other questions about the course or the project? I already see some topics probably can be published somewhere for next year's conference or journal. So I will, Professor Chen and I will contact you if your team is selected. Okay. Anyone would like to ask any questions or comment on the course? Anything you think we can, Professor Chen and I can improve on teaching the course? No? So far so good? Is it too easy or too hard? I think we are treating you guys pretty easily, right? Is the course material difficult? Because when we took robotics in outside of Taiwan, it's a very mathematics intensive course. I know Professor and I didn't give you a lot in the course material, but when we took the course, actually it's a lot of homework, mathematics, exams, and we want this course to be more practical. We want you to try building something, testing on something, and figuring out what are the issues. Okay. So I hope this training in the course will be helpful for you. Okay, so let's give ourselves a bigger round of applause. We finished the course. Okay. So how much time do you need for the final document? 1 week? Is 1 week enough? Do you know when is the last day for score submission? Second. So how about what is next Friday? Next Friday. How about next Friday, 29th? Please give us everything on before 29th. So whatever submitted after 29th will be thrown to the garbage. Okay. So please hand in everything before 29th. Okay. Okay. Thank you. Take care. Bye bye.